nice to be back, and thank you to the organizers for organizing it. I also want to make a comment before I get started. So most of this work sort of began during my fourth year of graduate school. So I spent a week visiting Zoe at ENS, and we spent many hours in her office each day. And so even though sort of I'm writing this, many of the ideas came from Zoe, and I just wanted to sort of acknowledge that. So the plan is to talk about classification theory and the construction of PAC fields. So most of the time in model theory we find fields, but this talk is going to be about building them. And here's the map that Gabe's gift to the model theory community. And the question that we often ask in model theory is sort of which parts of this map have a field in them. And if it has a field in it, what kind of field can it be? And of course, many of the hardest conjectures in model theory are about exactly this question, say the stable fields conjecture, the super simple fields conjecture, stuff like that. And I'm interested in building sort of counterexamples and finding new kinds of fields. So here is the SOPN hierarchy, just one part of the map. Maybe not the most interesting part, but it's there. So we say T has SOPN if there's some type, PXY, or you can make it a formula if you like, and an indiscernible sequence which is ordered by this type. So P, AI, AJ holds if and only if I is less than J. And if you take a sort of cyclic union, so P x0 through x1, x2, or x1, x2, x2, x3, all the way up to xn minus 2, xn minus 1, and then you loop back. So xn minus 1, x0, that's inconsistent. Okay? So the idea is you think about this as an instance of the order property, and you want to say, how close does this get to being an instance of the strict order property? And so as n gets higher, you're getting closer and closer to transitivity, because transitivity says exactly that you can have no loop of any size. So this says that you can't have small loops.
But do you mean complete type or?
Well, it doesn't matter. If it's in a complete type, then by compactness it reduces to a formula. So sometimes it's useful to have this formulation when you want to work with complete types, and other times when you want to do compactness arguments, it's useful to have a formula. So they're equivalent.
And bigger than 2.
Yeah, I should have said that. In bigger than 2, in at least 3. So for 1 and 2, it's defined differently, which is going to be something I mentioned many times in the talk. Yeah, so I should have said that. So there are going to be many theorems in the, well, not many theorems. There are going to be a few theorems in the talk that say something for SOPN. And when I say that without qualification, I really mean it for 1, 2, and n greater than or equal to 3. But of course, the argument has to be different for 1, for 2, and then for n greater than or equal to 3. OK, so this is the n greater than or equal to 3 case. I'm not going to define 1 because Byung-hun did that, and I'm not going to define 2 because we don't care. So here's the theorem. So I'm going to say the theorem first, and then I'm going to spend a lot of time sort of talking about the ingredients. So the theorem is just that the SOPN hierarchy is strict in fields. So let me say what I mean precisely by that. So for all n greater than or equal to 3, there is a field, which is SOPN, NSOPN plus 1. And in particular, it's a PAC field. So the SOPN hierarchy is not only strict in fields, it's strict in PAC fields, or if you like, PAC fields of characteristic 0. Moreover, there's an open problem. We don't know whether SOP1 and SOP2 are different, whether SOP2 and SOP3 are different. But if they're different, that will be witnessed by a field. OK. So maybe someone can prove something by coding them in fields. I'm very doubtful. But OK, this is the theorem. Now, the theorem's nice, but in truth, it's much less interesting, I think, than the construction. So the whole goal of the project is that we have constructions for coding combinatorial objects into, say, groups. You have something like the Meckler construction, which takes an arbitrary graph and produces for you a group which is nilpotent, step 2. And many of the model-theoretic properties of the graph are reflected in the group. Now, what I'm interested in is sort of an analogous construction for fields. I take a graph, I build a field out of it, and I want to know what are the model-theoretic properties that are preserved by passing from the graph to the field. And OK, the SOPN hierarchy is just a test case. But there are, I suspect, many other model-theoretic properties for which this construction will be germane.
Fields are pure?
Pure fields, so in the language of rings. Yes. Yeah, it's not so hard to find an expansion of a field with this property. You just put a graph on top. Yeah, so this is in the language of rings. I should have said that. Okie doke. So why do we care about PAC fields? So of course, the starting point is Axe's 68 paper, The Elementary Theory of Finite Fields. And he characterizes the pseudo-finite fields, which are defined logically, in algebraic vocabulary. So what he shows is that a field is an infinite model of the theory of finite fields if it satisfies these 3 conditions. The first is that it's perfect, which just says that if it's characteristic P, then f to the P is equal to P. is equal to f. It has Galois group z hat. And then the last one is this algebraic condition, which is the last missing ingredient, which says that f is pseudo-algebraically closed. So this was already mentioned by Samaria in her talk, but f is pseudo-algebraically closed if whenever you take an absolutely irreducible variety defined over the field, it has a point in the field. Okay, so algebraically closed fields are pseudo-algebraically closed by the Nostell-Ansatz, but you have lots more. So for example, ultraproducts of finite fields. Okay, so it became interesting within model theory to just ask how complicated can pseudo-finite fields be. So there was a question from the famous paper of Chatzidakis, Dries, and Macintyre, where they characterize definable sets in finite fields, about whether or not triangle-free random graphs are interpretable in finite fields. And Reshkovsky answered this question by showing that the Independence Theorem is satisfied in pseudo-finite fields, or more generally bounded PAC fields. And using the Independence Theorem, you can show that you have non-interpretation of triangle-free random graphs. So this is sort of the starting point of the theory. But Reshkovsky works in more generality. So recall that a field K is called bounded if K has finitely many degree n extensions for every n. And working in a general context where he studies definably closed sets in strongly minimal theories satisfying weak elimination of imaginaries and the definable multiplicity property together, if that definable closed set has a certain boundedness property, then the induced structure is super simple. So the upshot is that if you think about a bounded perfect PAC field, you can think about it as a definably closed subset of its algebraic closure, and that's strongly minimal, and it satisfies all the requisite properties. So in particular, he shows that a bounded PAC field is super simple. Now, the perfect assumption was later dropped in this paper of Chatzidakis Pillay on generic structures for simple theories. So in an appendix to that paper, they show that actually, if you drop perfect, of course, you won't have super simple, but you can still get simple. So a bounded PAC field is simple. And later, Chatzidakis showed that this is a characterization. So an unbounded PAC field has TP2. So a PAC field is simple if and only if it's bounded. So we know exactly which PAC fields are bounded, and that's a consequence of a certain Galois theoretic condition. And so there's a sort of emerging theme, which is already very, very clear in the work of Cherlin, Dries, Macintyre, which really sort of opened up the model theory of PAC fields, which is that you can think about a PAC field. Any question about a PAC field typically breaks up into two questions. One is about classical algebraic information, either about the algebraic closure or the separable closure in the imperfect case. And then you ask a question about the Galois group. And normally, if you answer those two questions, you can amalgamate them and answer whatever question you might ask about the field. So in particular, this shows up in sort of the characterization of types that Cherlin, Dries, and Macintyre show in their monster paper. And in order to give a precise meaning to what it means to ask a model-theoretic question about the Galois group, they introduced this inverse system. So of course, the absolute Galois group of a field is a profinite group. And that's not really a good object, a good model-theoretic object. For example, if you take an elementary equivalent group, there's no reason that should have an interesting topology on it or be profinite in any meaningful way. But you can think dually about the system of finite quotients and the maps between them, and encode that in some first-order structures so that if you take an elementary equivalent structure, then you can take the inverse limit of the associated system and get another profinite group. So this is really a way of fitting profinite groups into a first-order framework. So here's the definition. So you start with a profinite group, and you look at the set of open normal subgroups. And so the domain of the structure will be all of the finite quotients by open normal subgroups. Okay? Now, we're going to have a sort of strange multi-sorted presentation for this. So we won't have disjoint sorts. So this is what's a little weird about it. But we'll have a sort for every positive integer, and a binary relation less than, and C, which is, binary relation. So sorry, we have two binary relations, less than and C, and then a ternary relation P. So I don't know why these letters were chosen, or why this is the language, but this is the traditional approach. So S of G is an LG structure in the following way. So the coset, the elements of the sort Xn are exactly the cosets of open normal subgroups of index at most n. So notice that the sorts are growing, right? Because you get more and more cosets. Then you have a comparison. G of n is less than or equal to H of m if the groups, the subgroups have containment like this. then this C relation codes the projection. So if n is a subset of M, then whenever I take a coset Gn, I can project it and get a coset of Gm. And the graph of that projection is coded by this relation C. And then on each finite quotient, I have multiplication. And the graph of multiplication is coded by this relation P. So if I have n1, n2, and n3, and they're all the same, so these are all cosets of the same group, the same open normal subgroup, then the relation just holds if and only if I have the appropriate multiplication. OK, now this is a preorder, this partial order symbol. So I can take equivalence classes, and this is going to be the notation I use for this equivalence class.
Which one is preorder?
The less than relation. The less than or equal to relation is a preorder.
C is not just inclusion, that the coset Gn is contained in the coset Hn?
Well, so what this tells you is that if I look at Gn, and then I look at its image under the projection from G mod n to G mod m, yeah, I mean.
No, it's the same as the coset Gn contained in Hn.
Yeah. It's the same as contained into the coset, but I mean I prefer to think about it in terms of the maps. But sure, it's the same.
But each of these relations is defined only on a single source, right? So not on all the.
Technically, yeah. So okay, if we were to do this in the normal presentation, you would have disjoint sorts, and you would have bijections that sort of tell you the identifications between the disjoint ones, and then you would have a different relation for each sort. So even though you have a sort of globally defined partial order, it turns out that this can be like an omega. I mean, for certain groups, it'll be omega stable. Because we're cheating here. I mean, we're really thinking about this as only being sort by sort, but it's convenient to write it as a globally defined preorder because we all know how multi-sorted logic works. And, we can translate it if we like.
Your sorts are not disjoint.
If this, yeah, so here the sorts are not disjoint. So, but we sort of pretend like they are. It works, I promise. OK, so this is a certain structure. And I want to mention two sort of notions that are important in talking about this structure. So these are duals and subsystems. So suppose we're given L, K fields, and an embedding of the separable closure of K into the separable closure of L, so that L is a regular extension of the image of phi of K. So this is confusing, but imagine for a moment that this is just an elementary embedding of K into L, and then you extend that to a map on the separable closures. So that case will be the important one for us. So we have this embedding from Ks into Ls, and then this induces a map from G of L to G of K. So if you take an automorphism here, that is the same thing as an automorphism of the image of this by the isomorphism. So you look at the image of the separable closure of K sort of inside L, and then this tells you that that extends because of regularity. So this is an epimorphism, this map here. And then anytime I take a quotient of this, that's the same thing as an epimorphism from this to a finite group. So by composition, anytime I have a quotient of G of K, that gives me a quotient of G of L. So then I get an embedding from the inverse system of S of G of K to S of G of L. So this is an embedding which is called the double dual to phi. So each time the direction of the arrow switches. So if I do it twice, then I get an inclusion of the inverse systems.
So again, what is the last one?
This one? So the way you think about this map is suppose I have a finite quotient of G of K. So that's the same thing as an epimorphism from G of K to a finite group. But then by composition, I get an epimorphism from G of L to a finite group. And so that tells me how to map a finite quotient here to a finite quotient here. Or more generally, an open normal subgroup here to an open normal subgroup here. OK, does that make sense? OK, now subsystem, this would be the appropriate notion of substructure if the language was different. Now, a subsystem S you should think about this as a substructure up to an appropriate choice of the language. So what it means is that it's downwards directed and upwards closed in the preorder. In particular, it's closed under equivalence because this says less than or equal to. So you close under all the equivalence classes, and then you make sure that you're directed downward.
So the above you assume the image of phi is contained in L, not just in L.
Oh yes, sorry, I should have said that. So the image, yeah. I mean, I guess this is implied by being a regular extension, but yeah, yes, that is my intention. Yeah. So really, the example that you should think about is just imagine that L is a regular extension of K. So I mean, forget about k and think about phi of k. And then this is the inclusion, or this is rather the identity map. This is restriction, and this is dual to the restriction. That's the. I mean, you don't lose anything by thinking about that case. Okay. Okay. So let me tell you about this theorem, which I'm very enthusiastic about, and it's a monster. So I'm gonna draw a picture, and then everything will be clear. I promise. So here's a field f. I should not wait. Yeah. Okay. So f, and here's s of g of f, and we suppose that we have an instance of the hypotheses of the independence theorem in the field. So what does it mean to have the instance of the hypotheses of the independence theorem? You have a substructure, in this case this elementary substructure E. You have A and B, which are independent over E, and you have C0 and C1, which have the same type over E, and C0 is independent with A, and C1 is independent with B. These are the hypotheses of the independence theorem. And then by taking double dual, you get an associated map. I mean, an associated picture in the inverse system of the Galois group. So here's S of G of C0, S of G of C1. And suppose that not only do you have the hypotheses of the independence theorem here, but you also have a solution. So this gives you S0, which amalgamates these two things.
That's an assumption.
Yeah, so all of this is assumptions. So I start with the hypotheses of the independence theorem in the field F. I look at the associated instance of the independence theorem in the inverse system, and I assume that I have a solution. Then
if that was a solution here.
Then that means that there's a solution here.
Oh, I see.
So that S0 you can think of as SG of C. So we are asserting the existence of this. So the picture here, I mean, the way it's formulated is a bit complicated, but this is really the idea. So you start with an instance of the hypotheses of the independence theorem in the field. This gives rise to a similar instance in the inverse system. If you can solve it in the inverse system, then you could solve it in the field. So this tells you that amalgamation problems in the field reduce completely to the question of amalgamation in the Galois group. Okay.
What is G of C0? Is the Galois group of the field generated by C0? Or?
Yeah, so everything here, the way it's written is they're all algebraically closed subsets. So in particular, they're subfields. So they have Galois groups. So this is why it's a bit difficult to state. So you want to make sure everything is algebraically closed, so it makes sense to take the Galois group. But yeah, don't read this. Just look at the picture. And everything will be clear. So I didn't want to lie to you, but yeah, this is what it says. Okay, so here's a cool corollary. So Zoe proved in the paper where she proves this paper that if you have a PAC field and the theory of the inverse system of that field is inisopy n for n greater than or equal to 3, you get that the field itself is inisopy n. And then in my thesis, I sort of did the requisite work to extend that to 1 and 2. So in the case of n greater than or equal to 3, there's a sort of direct translation of SOPN into an amalgamation problem, because you want to show that this type, which is supposed to be inconsistent, becomes consistent. Now for n equals 1 and 2, for n equals 1, you use Kim independence in the Galois group and translate that and characterize Kim independence in the field. So a PAC field is inisopy n if and only if the Galois group is inisopy n, or if the Galois group is inisopy n. And then for 2, you use strongly indiscernible trees. So this is a somewhat different approach for the other two, but it's a corollary of the theorem I said before in a very direct way. So there's nothing deep about this extent. Okay, so this tells us that the question of whether or not we can build PAC fields with prescribed model-theoretic properties, at least for the question of SOPN, reduces to a question about the absolute Galois group. So here's the strategy. So we know that we reduced this to the absolute Galois group. Now what we want to do is we want to build groups. We want to build profinite groups that code graphs. And then, because we can find enough graphs, we can find enough groups. And then realizing those as the absolute Galois group of PAC fields, we win. We find PAC fields that are SOPN and SOPN plus 1. Okay, so this is the strategy. So what time do I need to finish, by the way? Do you remember? I mean, I can talk for
Half an hour.
half an hour. Okay, good. Good. So I'm on schedule. So I'll stop at 10:53. All right. So
25. So you started at 3 minutes. So yeah. So 10 to 12.
okay, 10 to 12. Yeah. Well, now we just lost 2 minutes. Yeah. Okay. So yeah. Yeah. Okay, doke. So, all right. Well, I don't know. I'll probably just talk, and then someone will tell me to shut up, and that's what I. Okay. So, so the idea here is to make use of a certain coding construction, which was developed by Cherlin, Dries, and Macintyre in their unpublished long paper on PAC fields. Now, their question was just about decidability. So they were using this coding construction for a very coarse kind of problem. They want to show that you can code graphs, and then you get some undecidable stuff in a PAC field, and then they were happy. Now, I want to just sort of reanalyze that construction with a more fine-grained approach and understand which sort of fine structural model-theoretic properties are preserved by this construction. So this construction is theirs, but the analysis will be a bit more refined. So here's the idea. So this slide will just set up notation. So we start by fixing, from now on, 2 distinct primes, odd primes, p and q. Now, CP will be my notation for the Z mod PZ, but thought of as a multiplicative group, which would be important just for notation. And OK, DP is the dihedral group. So this has 2p elements. It's generated by an alpha beta. So alpha is an involution. And if you conjugate beta by alpha, oh, sorry, that's a typo. This should say alpha beta inverse. So if you or alpha inverse beta maybe. Okay, anyway, what you want to say is that alpha inverse equals beta inverse. That's what it should say. So that's the same thing as the relation alpha beta inverse beta. Yeah, and there should be an inverse. So yeah, so there are a lot of things missing here. Yeah, so okay. So you want these relations. So alpha squared. So here are the relations. Alpha squared, alpha beta, alpha inverse beta, and beta to the p, and that's it. Okay? So a lot of things missing. Anyway, you know what the dihedral group is. Okay, so the relations are written here. Anyway, so you can okay, so there's a Z mod PZ sitting inside, generated by beta, and the quotient by that gives you an epimorphism onto the cyclic group of order 2, plus or minus 1, right? So let's call that tau. Now, using that, you can define an action from the product dp times dp acting on CQ by the following rule. So if I take a pair of elements from dp cross dp, x, y. Now, I look at whether their image in C2 is plus or minus 1. And I raise a to the power the product, tau x times tau y. So that means that if tau of x equals tau of y, then I do nothing. And if tau x is not equal to tau y, then I invert. That's the rule. Now, because I have an action here, I can define a semi-direct product. And W is going to be the semi-direct product with the action defined here. So that's W. And of course, this fits into a short exact sequence where W is going to be the semi-direct product of dp by Q. And just to give it a name, lambda is going to be this map that takes me from W to dp times dp. I just forget about the CQ part. OK. So now we want to build the graph. So first, start with a graph on vertices A and with edge relation R, and form the product, where you take a copy of dp for every vertex and a copy of W for every relation R, for every edge R. Then, of course, you can take any element of this group, which should be called H, as d bar times W bar, where this is a vector in dp to the A, and W bar is a vector in W to the R. And we have the associated projections. So I'm just setting up notation here. So pi of A is the projection onto the coordinate A. and pi r is the projection onto the coordinate r. And then we define a group G gamma as follows. So I look at the elements in this product. I look at the elements of this product. Yeah, so W is here. So it's the semi-direct product. So maybe I should just write this, because I think it's worth remembering. So W is going to be CQ, semi-direct product, dp times dp. Okay, so
can you also write quantization?
yeah, sure. So we have tau, which goes from dp to C2, which we're thinking of as plus or minus 1.
You mean CQ?
No, C2. And then dp times dp acts on CQ by x, y, acts on alpha by alpha to the tau x, tau y. So again, you take x and y, you look at their images under tau. If those are the same, then you do nothing. If they're different, then you invert. That's the rule. Sorry?
You have an H in the second.
Yeah, so I said that I had a typo. So H is what I'm calling D to the A times W to the R. Okay, but I won't use H ever again, so you don't need to worry. Okay, so G gamma is this group. So here's the way it works. So maybe one more piece of notation which is worth remembering is you have lambda, which goes from W to dp times dp, which is the thing that just forgets about the CQ coordinate. Right? So lambda here came from this. It came from this sequence. So here's lambda, which I'll remember here. So it's the surjection from W to dp times dp that forgets about the CQ coordinates. Okay, so here's the definition of the group. So I look at the vectors d bar, w bar, so that if I have an edge in my graph, which goes from A to B, then I look at the element in the r coordinate, and I take its projection in dp times dp. So wr, it's something here, so it's in a copy of w. So I can apply lambda. I can forget about the CQ part. Then I want that to match the dp parts. So if I have an edge from A and B, and then I look at the like the coordinate that is associated with the vertex, then if I look at the coordinate that comes from the edge and I apply lambda, then I get the coordinates that come from the vertices. They match. So this is the definition. And then just as a trivial remark, as defined, if the graph is empty, then you get the empty set here.
Is all this a group?
Yeah. I mean, this is a homomorphism, so it's fairly trivial to just check that it's closed under multiplication. It's also profinite because this condition is closed. So here you have a big product of finite groups, which is obviously profinite because it's by Tikhonov's theorem. It's compact, separable. I mean, it's compact, totally disconnected topological group. And then this is closed, so it's a closed subgroup of a profinite group, so it's profinite. So this is a profinite group, and this is just a sort of side comment. If A is empty, if the graph is empty, then in principle this definition gives you the empty set, which we don't want. So if it's an empty graph, then you just define the group to be the product of the vertices, and this coheres. Okay, so that's a group. Now. Now, I want to tell you an interpretation of graphs in profinite groups. So, given a profinite group G, which any one at all, I mean this might give you nonsense, but for any profinite group at all, you can define a graph, gamma G AR. So the vertices consist of open normal subgroups, such that the quotient by them is dp. Okay, and you say that there's an edge between N1 and N2 if they're distinct, and there's an open normal subgroup G, so that the quotient of G by M is W, and M is a subset of the intersection of these two open normal subgroups. So this is a fact that if you take the graph, you build the group, and then you interpret the graph again, you get the graph back. So this doesn't do anything. And there's a sort of nice picture of what this looks like in the inverse system. So the inverse system, you think of the sort. Oh, OK. OK, so in the inverse system, you have the sorts, let's say 1, p, 1, 2p, and 4p squared q. And I'm going to have several elements here, or really equivalence classes, which correspond to copies of dp. So these are like in and in 2. So these are elements of sort 2p in the inverse system. So this is S of g sub gamma. And I have an edge between these two things. If I can find some m here. So this picture tells me how to interpret this inverse system. So this interpretation, although I've described it in this language, is really an interpretation in the inverse system. OK, so this tells us how to build a group. But the real question is, can I possibly have this group as an absolute Galois group of a PAC field? If not, then it's not so helpful. So in order to talk about that, I'll have to tell you what a profinite group is. Or sorry, a projective group. So a profinite group G is called projective if it satisfies this following, is this property. So I take an epimorphism from G to A and from B to A. And what I want is I want to be able to complete the diagram with a homomorphism. So
is this projective for profinite groups? So
yeah, so it's the same thing as being a projective object in the category of profinite groups.
okay, so A is profinite.
Sorry. No, I really meant to say that A and B are finite. I mean, they could also be profinite, but yeah. So yeah, sorry. So A and B are finite. Thank you. Yeah. So it's known that you can't always complete this diagram with an epimorphism. That would be the natural guess for this. And notice that would be dual to the extension property that you're familiar with for say classes. So when you have the stronger property that you can complete the diagram with an epimorphism, that's called superprojectivity, or sometimes the Iwasawa property. And Zoe showed in her thesis that the inverse system of a group with the stronger property is omega stable. And so these are very, very nice groups. And the PAC fields, with those as their absolute Galois groups, are NSOP1, which is a consequence of the theorem I mentioned earlier, but it was known much before. This is something that Itai and I worked out. OK, so
Wait, but you wrote a detoned to. So again, what is the strong condition?
Shoot. No, I just used the wrong arrow. So yeah, OK, many typos here. So A and B are finite, and the text is correct, although the diagram is wrong. So there's a continuous homomorphism here.
Wait. A and B are finite. And A is an epimorph, B is an epimorph.
Yeah. OK, is that good? Cool. So we need to know the answer to the following question. What are the absolute Galois groups of PAC fields? So there's this sort of striking theorem of Van de Dries and Lubotsky, which shows that the class of absolute Galois groups of PAC fields is exactly the class of projective profinite groups. So secretly here, there's one direction which was known already to Axe, which is that if you have a PAC field, then its Galois group is projective. That occurs already in the 68 paper. So the thing that Lubotsky and Van de Dries do is they go the other direction. They show that if you have a projective profinite group, you can build a PAC field that has that as its absolute Galois group. So what we want now is a construction not that just takes a graph and builds a profinite group, but we want a construction that takes a graph and builds a projective profinite group, such that I can recover the graph from that group. So how do we build projective groups? So if you have a profinite group, there's a certain subgroup called the Frattini subgroup, which is denoted capital phi of H. And this is generated by the maximal open proper subgroups of H. So from the definition, you can tell automatically that it's a characteristic subgroup, so it's normal. And a Fertini cover is an epimorphism such that the kernel is, that should say phi of G. Yeah, so the kernel is contained in phi of G. Now, every profinite group has a universal Fertini cover, which is the same thing as the smallest projective group that surjects onto H. So this is defined, this is unique up to isomorphism. And here's a second key fact. If you take the graph, you build the group, then you pass the universal Fertini cover, and then you try to interpret the graph again using the interpretation I described before, you get the graph back. So actually, this process of replacing G with its universal Fertini cover does not affect the graph that we interpret in the inverse system. Okay, so this is wonderful, because what this means is that if we take this graph, we build the universal Fertini cover, then we can realize that as the absolute Galois group of a PAC field, and then we get what we want.
How does the second point make sense? The kernel is subgroup of G.
No, I clarified. Subgroup of G. Yeah, it's just a typo. It's a subgroup of G.
Or 5G.
Of 5G. Yeah, well, in particular, it's a subgroup of G, and it's also a subgroup of 5G. That one actually has content. Okay, is that good? Okay, so now I want to talk about how the analysis of these inverse systems of universal Fertini covers of G gammas go. So we want to understand certain important quotients of this group. So notice, for example, if I take n copies of dp, so I look at dp to the n, there's a copy of z mod pz to the n sitting inside. This is generated by the betas in each copy. So now if I take the quotient of that, then I get a big copy of z mod 2s. So I can quotient by this group, and I get z mod 2z to the n. Now sitting inside of z mod 2z to the n, as a normal subgroup, I have the diagonal subgroup. So these are the things which are either 0s in all coordinates or 1 in all coordinates. Wait, is this what I want? Yeah, I guess so. So what I want is the quotient to be z mod 2z.
So that's diagonal has two elements, right?
Yeah, so I'm not sure what I mean. Yeah, so there's a quotient of the z mod 2z which is, okay, so fix whatever normal subgroup makes this true. You have a quotient of this diagonal which, yeah. Yeah, okay, so I said nonsense here.
You just want to codimension one subspace or
something?
Not the same with respect to DM, DPM.
Oh, yeah.
Yeah. Yeah, I'm not sure what I had in mind when I wrote this. Okay, so anyway, let's ignore this for a slight moment. So here's one thing that is certainly true. So let me rewrite the fact in the following way. So let me write it on the board very quickly. So if you have a dp and a dp sitting at level 2p, and you take a 4p squared q, then there's a unique w sitting on top, if there's one at all. Okay? So this follows from the fact that in the graph interpretation, that the copies of dp you see are always associated with vertices. So every dp is really the kernel of a coordinate projection to a dp. And every w that you see is really coming from the kernel of a pi r. So all of the w's and the dp's that you see in the inverse system come from this configuration. So that means that from these dp's, there's a unique w that's sitting on top from the definition of the group. Now, I want to define a definition called the graph closure. And here's the way it's defined. So you define the graph closure A sub gr to be the smallest subsystem containing A, so that if you take an element and you get a z mod 2z, then you include all of the vertices that you see. So here at level 2, you might have a dp above, or it might be finitely many dp's above. So if you have a z mod 2z, which is a quotient of a dp, then you put the dp in. That's what this says. So if I see a element of this structure, and it gives me a z mod 2z, then I put in the kernel of the vertices that are associated to the C, meaning that surject onto the z mod 2z non-trivially. Now, additionally, if I have two things here which look like vertices, so which give me structures isomorphic to dp, so if I see two dp's, then if there's an edge between them in the subsystem, then I put that in the closure. So the idea here is I take the small substructure that sees every piece of the graph. So if I take a z mod 2z and I see vertices above it, finitely many, then I put those inside the graph, so they're all algebraic over the z mod 2z. And if I see an edge between the vertices that I put in, then I make sure that I put those edges inside this structure. So the whole point of this definition is that the interpretation of the graph applied to this substructure is an induced subgraph of the gamma that I've defined. Okay, so forget about this nonsense that was written before. This is really the definition. So this is just a definition. So it's a way of getting an induced subgraph from a certain set.
What is the stipulation? I didn't get it.
Which one?
Yeah, the first item, C. Yeah, then C.
Yeah. So sorry. So in the subsystem, I have this partial order, right?
This was that.
And then you have an equivalence relation, and on the equivalence class of a particular element, because I have this relation P, which is like the graph of multiplication here, this is isomorphic to a finite group. So each element in the inverse system, if I take its equivalence class, that is a finite group, and I can ask what group is it isomorphic to. Okay. So here, when I say C is isomorphic to Z mod 2Z, I mean I take an element, I look at the isomorphism type of the finite quotient associated to this class, which is given to me by P in the language of the inverse system. And if it's Z mod 2Z, then I look at which DPs are above. Yes. Okay. And then if there's an edge, I make sure that I put the edge in. Okay. So here's the theorem, which sort of tells us how to analyze types in the inverse system. So suppose I take two finite tuples from the inverse system, and I look at the graph closed substructures that they generate. So this is a subsystem which is graph closed. So it means that the interpretation of the graph here is going to be an element, an induced subgraph of gamma, and the thing here will also be an induced subgraph of gamma. And I look at the induced map, which goes from gamma A to gamma B. So I first take these substructures, I form the interpretation of the graphs, and I look at the induced map between those graphs. And I ask the question, is that partial elementary? So if that's partial elementary, in the theory of the graph, then actually the map that sends A to B is partial elementary in the theory of the inverse system. So this tells you exactly how to analyze types in the inverse system. All you have to do is understand types in the graph and the quantifier free type in the inverse system. And using that, you can...
What did you say, quantifier free?
Well, because the quantifier free type is encoded by the isomorphism type of the substructure generated by the tuple. Right? It's sort of like in Frisé limits, right? Like two things have the same type if there's an isomorphism of the structures that they generate. Okay, but okay. So quantifier free type is not strictly speaking true because the language is not correct, right? I mean, like the substructures don't correspond to subsystems, but you think about it really being secretly quantifier free. I mean, you can formulate an appropriate language in which it's quantifier free, and it's not too bad. But okay, really, I mean, the isomorphism type of the substructure, which we think of as model theorists as coding the quantifier free type, but up to an appropriate choice of language. Okay, and then using this analysis of types, you can prove that for all positive integers n, here I was careful to write it, that the theory of the inverse system of the universal Frattini cover of the group that you build from the graph is anisopian if and only if the theory of the graph is. So this is enough to tell you, I mean, not really the theorem, but really the proof of the theorem tells you how to analyze types. And you can code the relevant amalgamation problems in terms of the graph and then solve them. Okay, so now let's just put it all together. And yeah, this is right on time. So for n greater than or equal to 3, there are graphs. There are known examples of graphs these loop-free graphs of a certain kind, which are SOPN and NSOPN plus 1. So you just build the right graph. Now, there's a general fact which is easy to show, although I don't know if it's written anywhere. Well, I mean, I wrote it down, but I don't know if it had been written before anywhere else. Is that if SOP1 and SOP2 or SOP2 are not equal to SOP3, this will be witnessed by a graph gamma. And to prove this, it's very simple. You just open up your copy of Su-Gauss invariant descriptive set theory, and you look at the proof that graph isomorphisms are all complete. And what you do is you just code arbitrary structures into graphs. And it's very simple to show that SOPN, for example, is preserved under this operation because essentially definability is not changed.
Structure is by interpretable.
What?
Every structure is by interpretable with the graph.
That's the idea. Yeah. So
Well known.
yeah, but okay. There's a small check. I mean, I was clear that it's trivial. I mean, it's not a deep fact. Okay, so then you build G gamma from that graph, and then you pass the universal Fortini cover, and we know that that operation preserves the graph. Then you use Van den Dries-Lubatsky, the inverse Galois problem for PAC fields, to realize G tilde gamma is the absolute Galois group of a PAC field. And then gamma is interpretable in the field. So this is something which...
What is G gamma tilde? Where did you construct this?
Well, this is the universal Fortini cover of the group G gamma. Then gamma is interpretable in the field. So this is a somewhat delicate point in the sense that SG of gamma is not actually interpretable in the field gamma because it's the Galois groups are really only interpreted up to conjugacy. So SG of gamma is interpretable in the pair, the field together with its algebraic closure, or the field together with its separable closure, but not necessarily in the field itself. However, the graph is interpretable because you can write polynomials that say, I'm separable and my Galois group is dp, and I'm separable and my Galois group is w. And using that, you can code the graph even if you can't get your hands on the Galois group itself. And so this gamma is interpretable in the field, and so F is SOPN, but then also it's NSOPN by this theorem of Zoe, which shows you that if the group itself is NSOPN, then that passes to the field. Oh shoot, yeah, NSOPN n plus 1. Yeah, this would be a remarkable theorem, right?
So where did you use the theorem about amalgamation exactly?
So which one? Zoe's theorem?
No, you. I mean the one, the big one.
Here.
That's Zoe.
I mean, so for this one, this is me, and then this one is Zoe. So look, so there's two steps, right? So one is that you have a graph, then you get a group, and then you have the group, and you get a field, and then you want to prove that NSOPN is preserved at each step of the way. So I start with a graph and I build a group. I show that if you start with an NSOPN graph, then you get an NSOPN group. Zoe shows that if you start with an NSOPN group and you build a field, you get an NSOPN field.
That's right. This big theorem, this what you call.
Yeah. So
this one, yeah.
Yeah. So this theorem is a corollary of this theorem because you code SOPN as an amalgamation problem.
Right, but you only use this theorem for n equals 1 or 2 or what?
No, you use it for all three.
But then you,
So you have to use strongly indiscernible trees or chem independence to do the 1 and 2 case. It's not such a direct translation, but you translate everything into an amalgamation problem and you cite this theorem. Okay, so Enrique's standing up, so I should stop. But thank you.
Questions?